What's going on, everybody? Mr. Diamond back. We are going to continue with Section 2 of Chapter Zero's notes. When we last left off, we were talking about the structure of the atom and the history of the atom and the discoveries that kind of led up to it. We talked about J.J. Thomson discovering the electron and the Thomson plum pudding model of the atom. And I said we were going to stop here because this was something that I really enjoyed talking about and going into a lot of detail on. And that was Ernest Rutherford and his gold foil experiment. So the nucleus as a whole, not the individual pieces, but the nucleus as a whole, wasn't discovered until 1911. Up to that point, based on the plum pudding model of the atom, they thought that it was kind of a cloud of positive space with little negative dots. Those were the plums, and then the positive space was the pudding. Remember, it's like a baked good, not actually like pudding. And Ernest Rutherford did an experiment in 1911 that disproved that as the overwhelmingly known theory of how everything worked. And it gave us most of our insights into the composition of an atom. Some lovely raspberry tea, by the way. So what Rutherford did was he took a very thin slice of gold foil and he shot alpha particles at it. Now, if I asked you what would happen if you shot alpha particles or if you shot anything at a piece of metal, I assume you would think that it's just going to bounce off. That seems like that's a very obvious answer, like no duh, Diamond. Like we've been doing this our whole life. Anytime you have like a bouncy ball or anything like that, like heck, it's a wall behind me. Let's try it. Nope, didn't go through the wall. So if you throw anything at a hard surface, let alone a metal surface, you would expect that it's probably going to bounce off, or maybe it'll bend the thing, or do something like that. Maybe it'll splat into it. But obviously we wouldn't be talking about this if that was actually what occurred. So this was the setup that Rutherford had. He had let me get my cool pointer going. He had a lead block that contained a source that emitted alpha particles. Alpha particles are basically small positive pieces. It's the same thing kind of as a helium nucleus. And they basically had something radioactive inside this brick of lead with a hole drilled in it, and the only possible way that something could escape from that block was if they kind of were going in a straight line out of it. So they built a gun of alpha particles by doing that. Then they had their small piece of gold foil here. Now they used gold specifically because it was unreactive. It's one of the most unreactive elements on the periodic table. Not as unreactive as the noble gases, but I don't know if you've tried to make like a sheet of gas, but that doesn't actually really work. So the beam was going to be fired at the piece of gold foil, and then he fully encircled this with a zinc sulfide coated screen. You can almost think of it as like a mood-changing paper, where if it gets interacted with by alpha particles, it will actually change color. It would actually detect and show up on the screen. So you would expect that as the beam comes and hits it, that it would bounce back, and it would be going back to these areas over here on the screen. And that did happen, but that only happened to approximately like 1% of the actual particles that were going through there. 90% of the particles passed straight through the gold foil with little to no change in their actual trajectory. They just, bam, straight through. And then only 9% were deflected at an angle. So we've got about 90% of them right here. We've got about 9% over on this side and over on this side. And then about 1% in the place we thought that they would obviously go, 1% of them went there. To which Rutherford was like, what? That seems really weird. There's a couple of reasons that you could maybe logic that through. So, okay. Well, we think that the nucleus has a big positive area. I guess maybe that positive area is just a cloud. It's not even actually a physical thing. But if that's the case, then how come these things were able to bounce back? That doesn't make a whole lot of sense. Well, if it's not a cloud, then it is a solid thing, which would explain why it bounced off. Then why are most of them passing straight through? That's a lot of weird questions that he did not quite know the answer to. So he sat and he thought about it, and he talked to some of the people that he knew that was on his level and studying the same kind of material. And eventually, he arrived at 3 conclusions. And if I saw this happen, I would just be like, I did something wrong. There's no possible way. This doesn't make sense. Something must have gone wrong in this experiment. I'm just going to pretend it's not what happened. But because he was way smarter than any of us are at this point, and because he was a scientist back then who was working really hard on this, he logicked his way through what could be happening here. And he came to 3 conclusions. He said that, first of all, because of the fact that it's all just passing straight through, or most of them are, most of the atom must be empty. Like, there must be basically almost all empty space. There just has to be at least one small area that things could be interacting with. And because the particles shot at the screen were positive and they were deflected, if you have a positive coming close to a positive, let's say this is my nucleus and this is my positive nucleus. If my beam comes close to it, but my beam does not hit it directly, and it's not super far away from it, but if it gets close to it, you probably already know what happens when 2 positives get close together. Well, they get pushed away, and this nucleus is locked into place because it's a piece of the metal, but this beam can then get bent, and it can kind of go off on a different side direction. And because of that, he said, well, if it was negative, it would just be attracted to it. So I guess whatever is in the middle there, whatever hard, solid piece there is, must be positive. And that's why it's deflecting the beams. If we go back, that's why we're getting this bend, because as it gets close to it, it's kind of pushing it off to the side. And then there must actually be something that's dense in there, because that's what it would be bouncing off of. So that nucleus, that small positive place, must be very dense. And this actually made sense and is pretty much how we believe that the atom works now, or at least is getting a lot closer to how it works now. If you look at this kind of model here, most of them are just going to be able to pass straight through. If they get close enough to the nucleus, they could be affected by the positive. They'll kind of get deflected at angles, some of them greater than others. And then only if you square bullseye the nucleus, if you hit it exactly dead on, will it bounce backwards to you. So 90% of the time it'll pass straight through. 9% of the time it will be deflected. 1% of the time it will bounce back. And then his conclusions make sense. Because most of them pass straight through, it must be a mostly empty space. Because 9% of them are deflected to the side, it must be positive. And because 1% bounce back, it must be a dense, solid, positive dot in the middle of it. Now, his model had some flaws, but now we're starting to look at what we actually think of as an atom. You've got a dense, positive nucleus, a whole bunch of empty space, and electrons floating around the outside of it. Protons weren't discovered until the early 1900s as well. This was Henry Moseley. He was one of the pioneers in the field of radiation. He was using X-ray crystallography to be able to actually try to count the number of positive charges that were inside of a nucleus, and he assigned that because there was, in one atom's nucleus there was 5, and the other was 6, the other was 7, and there was individual pieces, he said that piece must be a proton. It must be a positive piece that is inside of each of them. Neutrons was the hardest one to find, though, and it wasn't until the 1930s James Chadwick figured out this last piece, which, by the way, that's like pretty recent. That's less than 100 years ago was when we discovered the neutron. We usually think of these things as being like, oh yeah, we've known about them for like a super long time, but like you could know people in the real world, not online or anything like that, that like were alive before we knew what a neutron was. And it was hard to find, though, because it was not charged. If you remember, electrons were found because we were using electricity and it was able to be deflected by negative charges. The proton was discovered because they were counting positive charges. The nucleus was discovered because it had a positive charge. That's part of where its characteristics came from. And so since neutrons don't have a charge, it becomes really, really hard for you to actually be able to figure out. Basically what they did was they were bombarding certain elements with radioactive emissions and alpha particles, and they knocked stuff out of the nucleus, but the nucleus stayed the same charge. And so they realized, oh, there must be something else in there other than just these protons, these positive pieces. And so they called them neutrons. A neutron is a combined proton and an electron. So it's actually the heaviest of them. We're not going to really worry about that too much in this class, but a neutron is actually formed by a proton and an electron smushing together. It will make a neutron. I apologize for the yawn. It's early in the morning when I'm recording this. Okay, now we're on to Bohr's model of the atom, and I apologize if this is a little bit boring. I'm so funny. This is probably about the level of the atom that you guys remember being taught in any of your classes you probably got through. Bohr realized electrons could not simply be floating randomly around the nucleus. The big problem with that was because if they were, why wouldn't they just be like falling into the nucleus? Like, it doesn't make sense that they would just be floating around there. If the nucleus is one dense positive space, they should be getting attracted to that positive space and spiraling in. But Bohr realized there must be some kind of specific energy present that is helping keep these electrons more or less within their orbit. If you have a certain amount of energy, you get to be a certain distance from the nucleus, and then you can maintain that distance because of the speed and the energy with which they're moving. We'll discuss energy levels in more detail later. Actually, I think it's next chapter. I modified this a little bit. So we'll be discussing these energy levels a little bit more detail next chapter. But that's what these rings represent, are the different energy levels, and each energy level can have certain electrons in them. Currently, this is actually the closest representation of what an atom looks like, thanks to the work of Louis de Broglie, Werner Heisenberg, Erwin Schrödinger, a lot of other people. We realize electrons don't actually act in clean, pretty rings. Instead, they occupy big clouds where we basically say, yeah, it's in here somewhere. Which seems weird because we used to have very specific, like, it's in this ring right here, and now we've gone back to, like, it's somewhere in here. But because of the nature of electrons and of subatomic particles, we really can't get any better than that. We'll talk in more detail about what orbitals specifically are, but basically they are just, here is a big area, and the electron is probably in this version of that area. And for this different electron, it's probably in this version of this area. It's just giving you a cloud where something is most likely to be. It'd be kind of like if I said I wanted to figure out where you were, and I could say, well, like, you're probably at home or at school at this point. Maybe at work if you have a job. Between those three places, I've probably covered 90-ish%. But sometimes you're moving between them. Sometimes you're going to other random places. Sometimes you're going to the store. Sometimes you're going out to eat. Although that, I guess, a lot less nowadays. But still, I could say with a decent amount of probability where you are at any given time is probably work if you have it, otherwise school in your house. So basically, this is something that someone sent me last year that I thought was pretty funny. All of these models just keep absolutely murking all of the other models and taking them out, replacing them. We had the plum pudding model replaced by Rutherford's model. Rutherford's model was replaced by Bohr's model, and then quantum mechanics and Heisenberg's uncertainty principle and all of the other crazy stuff is out here to absolutely decimate Bohr's model and completely upend everything that we had. I believe that brings us to the end of the section. Section 3 is going to get us into an introduction to some periodic table stuff. I'll probably modify this slide right after this video is over because I think it cut off the other word. I hope that makes sense. The gold foil experiment is going to be very important. There will definitely be a test question about it, so please make sure you go back and you understand kind of the stuff that I talked about, both what it was, how it worked, what was the important parts of it, how did he come to these conclusions. All of those are super important. If you have questions, shoot me an email or stick around for one of the Zooms at some point. It's definitely been a lot more busy in class than I've expected, so it also looks like not a lot of people are joining the Zooms, though, so that makes me feel at least a little better that I'm not missing out on the time. Otherwise, you can Zoom in on Friday to ask questions, but I hope you guys have a great day, and I hope to see or hear from you soon.